Hello, the title of our paper is LT-GAN, Self-Supervised GAN with Latent Transformation Detection. So, generative adversarial networks are one of the most popular generative models today. And in this paper, our objective is to improve the training process of generator in standard GAN training procedure for two reasons. First, for better organization of the latent space semantics, and secondly, for improved image quality and diversity. So, why is latent space manipulation important? As shown in the first figure, it allows us to perform interpolation in the image space, like changing the facial pose of a person smoothly. As shown in the second figure, it allows us to perform semantic face editing, like changing certain attributes of the face like age, gender, eyeglasses, etc. And as shown in the third image, it allows us to perform a series of transformations in the image space in order to achieve a desired result image. So most of the prior work has focused on using a limited set of certain predefined augmentations or transformations in order to define the self-supervised task. As shown in the figure, here is SS-GAN, which uses a rotation-based self-supervision loss. Now we'll describe latent transformation detection as a self-supervision task. So if we have a random latent code Z1, we can get the image as G of Z1. Now we perturb the latent code Z1 by adding a noise vector of small magnitude, that is epsilon1, and getting the resultant image as G of Z1 plus epsilon1, which we define as the GAN-induced transformation of the original image, that is G of Z1. So now the self-supervision task is a binary classification task in which, given the feature representations of the two pairs of images, where each pair consists of the original and transform images, the aim of the self-supervision task is to identify whether the transformation in the first pair is like that of the other pair of images or not. So the self-supervision loss is used to train both the auxiliary network and the generator, both of which are trained in alternation with the discriminator, and hence the generator is encouraged to produce semantically consistent images when perturbed with the same noise vector. So now here are some of the results using FID metric. We use three datasets, CIFAR10, Self-HQ and ImageNet, and we use three GAN architectures, Big GAN, SNDC GAN and Style GAN. We also combine LT-GAN with the current state-of-the-art regularization approach, that is consistency regularization, and as you can see, in both class conditional and unconditional settings, it helps us to improve the FID. Now we present semantic image editing results for Self-HQ dataset. So using the framework of interface GAN, we find linear boundaries in the latent space corresponding to binary attributes like age, eyeglasses, gender, and smile expression. We do this by training SVMs, and a higher SVM accuracy is desirable since it means that the latent space is more steerable and disentangled, and it allows us to have better control over the image editing process. So as shown in the table, for both SNDC GAN and Style GAN, LT-GAN is able to achieve a higher accuracy as compared to the baseline on all four attributes. Here are some of the qualitative results for LT Style GAN. So now we present results for semantic image editing on ImageNet dataset. So the figure is divided into two halves. The left half represents the interpolation result for baseline Big GAN, and the right half represents interpolation result for LT Big GAN. We use 5 ImageNet classes: car, ball, bird, mushroom and burger, and the images that are shown in the center, which are highlighted in red, are the original images, and then we show the zoomed out and the zoomed in versions on the left and right of the original image respectively. So as shown in the figure, LT-GAN results in smoother and more meaningful transformations in the image space while preserving the content of the image and avoiding distortions at the extremes. Now we show that LT-GAN helps improve the GAN training procedure using classification accuracy score, that is CAS, which is an additional metric for evaluating conditional generative models like Big GAN. Here we use a standard image classification network like ResNet and train it using the data generated by a GAN, and we then report its accuracy on the real test dataset. So on CIFAR10, LT-GAN achieves a CAS of close to 80%, while it's only around 71% for the baseline model. Similarly for ImageNet, LT-GAN achieves a top 5 accuracy of 49%, while the baseline model achieves only around 44%. So many classes in baseline Big GAN suffer from severe mode collapse, which is alleviated to a large extent in LT Big GAN. Here we show it using 4 ImageNet classes: clock, nematode, parachute and fish, and as you can see, the baseline Big GAN images are exhibiting lower diversity and poor quality, while the LT Big GAN images are exhibiting much better quality and diversity. So finally, to conclude, LT-GAN is a novel self-supervised technique based on the idea of GAN-induced transformations, and it has two benefits. First, better organization of the latent space semantics, and second, improved quality and diversity of image generation process. Thank you.